It looks like a symmetric curve, bell-shaped, inverted bell-shaped curve. Highest probabilities are in the middle, and then in both tails, right tail or left tail, the values keep on reducing. If you capture the amount of time somebody watches YouTube or Netflix, so that time is likely to follow normal distribution. Or if you count number of likes someone gets on Instagram for every post, so there could be some posts where you get a lot of likes, there could be some very few, and there could be some where it is really very high. But most of them are in middle. I have like a small YouTube channel, so there when I post videos, so there are some videos that get a lot of views, some videos will hardly get any views, and most of them will be somewhere in the middle. A number of hours somebody sleeps in a day, so if you capture that data for like 30 days or 100 days, you most likely will get this kind of picture where some days you get up early, some days due to whatever reason you get up slightly late, and most of the days you sleep on an average at a very high probability. This distribution is symmetric, as I said. If you draw this line, so area to the right, area to the left, 50-50. So if you cut this distribution from the middle and fold it, both sides will overlap nicely. It's not that in real world every data or every random variable that is continuous and likely to follow normal distribution will be perfectly like this. It will be some approximation of this. So when you look at any normal distribution like this, in the background you can imagine that there is some data, and using that data you create a histogram, and that histogram, if you remove the bars, just use the curve. So that's the pattern we are drawing here. You have mu or mean and sigma as two parameters for normal distribution. So we write x follows normal distribution with mean mu and standard deviation sigma. Now if mu changes, if mean or the central location of any data changes, the change may look like this. For some variable x, so the distribution will shift on the lower side or higher side depending on how much this mu changes. Assuming that variability is same. So variability is captured by how much wide this distribution is. If sigma changes, assuming like mu remains same, then you may have something like this, where you have a normal distribution like different shapes, but overall they have their peaks in the middle. I'm trying to draw like same mean but different variabilities. So suppose this is 1, this is 2, and this is 3. So which one has the highest standard deviation? Yeah. 1, because you see spread is more. Don't go by like this height. So this one is very thin. So thin means less variability. And wider means more variability. Just like in your histogram, if you have like a lot of variability, there will be a lot of spread in the data. This one has max or maximum sigma, and this one has minimum sigma out of the 3. If this is your x-axis, and if I draw this normal distribution, that line starts to go up, reaches a peak somewhere here, where you have this mu, then it starts to fall. But when it starts to fall, it doesn't follow the same pattern, because if you allow this to fall, it will fall here. But somewhere there it changes direction. It changes direction in such a way that it starts to slightly go away from x-axis. So this point is called point of inflection. The change that is happening is the point of inflection, and if you drop that on x-axis, so that is the distance from mean, which is your sigma. So one standard deviation from mu to this point where it changes direction. So this is mu plus sigma. Similarly, you have mu plus 2 sigma, mu plus 3 sigma, mu minus 2 sigma, and then mu minus 3 sigma. If you convert x into z, if you recall in the second chapter, we made use of z-score. So sometimes people also work with z. So z is equal to x minus mu divided by sigma. So if you do that transformation and convert this x-axis to z-axis, x minus mu, so mu minus mu becomes 0 divided by sigma. So let me just draw a line to indicate this is z-axis for the same curve. So this becomes 0. If you plug in this value, you get 1, 2, 3. Similarly, negative 1, negative 2, negative 3. So this is true for any distribution. Whatever may be x random variable, so x may be following how much you sleep. You convert it into z, it will have same axis. Or if it is like how much Netflix somebody watches every day or every week, or if you have a random variable which is measuring thickness of a tabletop in millimeters, and you convert that into z, again the values will look like this on z-axis. So z-axis basically standardizes every normal distribution. That's why this distribution for z that we get is named as standard normal distribution. Standard normal distribution, if I have to write, z follows normal distribution, mean will be 0, standard deviation will be 1. Always, irrespective of what is x, your z will always have mean of 0 and standard deviation, like this gap, is always 1. Now, how much is this area on this curve? If you draw this line here, so that area in between one standard deviation from the center. So that area for normal distribution is approximately 68.2. 68.2%. If you go further one step, plus minus 2 standard deviation will be 95.44. And if you go plus minus 3 standard deviation, so this distance is 99.72. So from here to here, almost everything is within the curve, under the curve. So out of 1.9972 roughly for normal distribution, that area is under the curve. Let me write down those 3 situations. Example 6.3. The final exam scores in statistics class were normally distributed with mean 63, standard deviation 5. A, find probability that a student scored more than 65. We are given that x follows normal distribution with mean 63, standard deviation 5. So this is a low scoring exam. Average is only 63. It's not like our class, I guess. Our average was like 92. So very far away from maybe some other college, some other school. So 63 and 5, we are interested in what is the probability that x is more than 65. If you make a picture it looks like this. Mean 63, standard deviation equals 5. 65 is to the right of 63. So somewhere here, and more than that means we are interested in this area. So if I give you this situation and give you a quiz question, is this probability more than 0.5? What will be your answer, like if it is true and false? Without calculating anything, is this probability more than 0.5? Obviously that's a false statement. Because visually you can see, you know that area to the left of 63, area to the right of 63 is 50%, 50-50. So this looks very small compared to 0.5. We are interested in this area. I will do that very quickly, but let's also look at B. 85 may be somewhere here, and less than that means this area. So we are interested in this. Our standard deviation is still 5. Now to solve this problem, we can go to our friend. While we are here, I'm going to create a new file. Go to File, New, R script, and then save as, because we are moving on to chapter 6 now. Chapter number 6. So chapter 6 is normal distribution. So it is a continuation of last chapter, because normal distribution is something very important in statistics, and we are going to continue to use it in many more applications. So they have dedicated entire chapter to normal distribution, but this is also a continuous probability distribution where your random variable x takes continuous values. So area to the right, so probability NORM, so area to the right is 65, so we give 65, 63 is the mean, standard deviation is 5, and this is in the right tail, so we have to say lower tail false. So this is the second situation that I wrote. So this is false. This is part A. So that area is 0.344. To create a picture, let's start by saving the information. Mean is 63. Standard deviation given is 5. The point of interest on x-axis is 65. Let's store in x a sequence of numbers, mean minus 3 times standard deviation, mean plus 3 times standard deviation, and we can increment this from the lower value to higher value by 0.1. So this will be the lower value, lower tail, this is upper tail, 3 standard deviations away from the mean, and then we increment by 0.1. So this should be SEQ, sequence. In Y we will store normal distribution values. So D for distribution or density, NORM. So values of X, mean, and ST. So using that we can plot a normal distribution. So let's plot Y goes on Y-axis versus X. So if you run this, you get a normal distribution plot. We can change the style from circles to line. So within quotes line L. So this will look better as normal distribution. And now we want to include the shaded portion, 65 and above. Within X I am going to store sequence. So the minimum value for the shaded part is X1, and we will take it to the maximum here, increment by 0.1. In Y we are still using the same distribution, so this will have X values, so these X values will go here, and then we create a polygon So starting with for x values, we can say x1, x, and that upper value mean plus 3 standard deviation. Similarly for y values, we can simply say 0, y and 0. And we can choose any color we like. So let me choose blue. So basically it shades values above 65. Similarly, second one less than 85, so P, N, O, R, M. And less than 85 means mean is same, 5, that's it. 0.9999, so almost 99% chance that if you pick up a student randomly, they have a score of less than 85. So this area was 0.345. And this one we got almost like 1. Almost 100% that if you pick up a student from that class in that exam, they got less than 85.